Let's look at ideal of a ring. A non-empty set, more precisely, subset S of a ring R is said to be an ideal, or to be more precise, two-sided ideal of R if these two conditions are satisfied. One is that S is a additive normal subgroup of R, and the second is for all S belonging to S and R belonging to R, both R S and SR belong to S. So if these two conditions are satisfied, then that subset of S is called an ideal. And importantly, S, which is an ideal, is a subring of R. Okay. Now, unit ideal, where the ring itself is an ideal, and zero ideal, the set containing only zero of R is an ideal. So these are also called improper ideals. Okay. So if we go back a little bit, you might realize that it is quite similar to the normal subgroups of a group. And we know that we use normal subgroups to form quotient groups, or also called as factor groups, okay, which we represent it as G by N or G mod N. Now, if G is an abelian group, we also know that all the subgroups of G would be normal subgroups. Okay. Naturally, if there are no normal subgroups of a group, then we can't form quotient groups. Okay. So therefore, ideals can be used to form cosets in a ring. The elements of this would be cosets. Similarly, here ideals can be used to form cosets in a ring, and we can represent it as R by S or R mod S. Now, naturally, the question comes, when is R by S a ring? Yeah, here I have already mentioned the two conditions, right? In which case, in any ring, this would always be the case, additive normal subgroups, because as per the definition of the ring, it is, abelian, right? So, remember, using this, we can form cosets of S, and it would look something like this. Let's say R is an arbitrary element of R, then R plus S is going to be, this is the coset, is going to be the set R plus S, where S belongs to S. And remember, cosets are always formed under addition in a ring, in case of rings. Here, remember, R is abelian group for a ring. What are the conditions? It should be closed under addition. It should be associative. It should have an identity. It should have an inverse, right? And it should be commutative when it comes to addition. S is an abelian subgroup of R. Because if R is abelian, then all its subgroups are going to be abelian, which implies that S is a normal subgroup of R, which implies R by S under addition is an abelian group. Okay. Now, remember, we have to figure out what condition has to be satisfied. So let A comma B belong to R. Since it is an abelian group, we don't have to bother with addition now. What we have to figure out is under multiplication also whether it is possible. So let's see. A and B belong to R. So which means if we form a coset using A plus S and multiply it with another element of R by forming its coset, we should get a coset, right? So which means the product of two cosets should form a coset of R by S, right? So let's see. For all S prime belonging to S, A plus S times B plus S prime should belong to AB plus S, which implies, now let's open up this. So AB plus AS plus SB plus SS prime belongs to AB plus S. So here AB gets cancelled, left cancellation law. We are left with AS prime plus SB plus SS prime belongs to S. Now, if we take SS prime to the other side, it gets absorbed into S. Any operation we do with an element of S, the result remains in S. So, which means AS prime plus SB belongs to S. When will this be true? When will AS prime plus SB belong to S? When both of them individually belong to S. So, which implies that AS prime belongs to S and SB belongs to S, right? Or in general, we can say R by S is a subring of R if instead of using A and S, what I'll do is I will replace A with R, an element of the ring. So R, S, and again S, instead of saying SB, I will say S and an element of R. So SR. They both belong to S, which is what the definition says. Yes. For all S belonging to S and R belonging to R, both RS and SR belongs to S. Clear? Now let's look at some examples. Let's look at the ring of integers. And let's see some ideals of this. So let's take any number. So this is the representation, parenthesis, within that an element of R. This would generate a set. So that is 3n, where n belongs to z, which is equal to this. In short, we can also write it as 3z, which is nothing but all the multiples of this. Is pretty, every element would generate its own multiples. Now let's look at something more interesting. Let's look at Z15 and let's take 2 as the generator of the ideal, or let's generate the ideal using 2. So this will give us 2n, where n belongs to Z mod 15. Now what will this give us? It will give us 0, 2, 4, 6, 8, 10, 12, 14. Now, generally we stop at this point, but here we are not going to stop. We'll keep going. Till when? Till we get 0 again. So 2 8s 16, 16 mod 15 is 1. 2 9s 18, 18 mod 15 is 3. 2 10s 20, 20 mod 15 is 5. And you can see how it goes. 7, 9, 11 and 13. Next term would be 15, which we can't include. That is 15 times 2 is 30. 30 mod 15 is 0. So we come back to 0. Okay, so if you notice here, all the elements are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, including 0. Right? So, which means this is equal to Z15, the entire ring. Okay. Since it generates the entire ring, so since 2 is equal to Z15, 2 is called the unit of the ring, which basically implies that 2 has an inverse, right? And what is that inverse? If you look at this 8, 2 times 8 is 16. 16 mod 15 is 1. So 2 times 8 is equal to 16, which is congruent to 1 mod 15, right? So product of two elements is equal to 1, means that this is the inverse of this and this is the inverse of this. They are the inverses of each other. Okay. Now, let's take one more example. 6. This is going to provide us what? This is going to provide all the multiples of, right? So, where n belongs to Z, 15. This would give us 0, 6, 12, 18. 18 mod 15 is 3, right? Again, 6 times 4 is 24. 24 mod 15 is 9. 6 times 5 is 30. 30 mod 15 is 0. So we come back to 0, so we can stop. And this is not equal to the entire ring, in which in this particular case that ring is nothing but Z. So you might have noticed that here we have the entire ring being generated. Here entire ring is not being generated. So here it is a unit, here it is not. Now another interesting aspect is, let's take 7. Okay, now what will this do? 0, 7 1 7 mod 15 is 7, 7 2 is 14, mod 15 is 14, 7 3 is 21, 21 mod 15 is 6, and if you continue doing this, you will get 13, 5, 12, 4, 11, 3, 10, 2, 9, 1, 8. So again, this is equal to the entire ring. 2 and 15, 15 of this and 2 of this is relatively prime. Similarly here, 7 and 15 are relatively prime, whereas 6 and 15 are not relatively prime. Okay, so here again, which means that 7 is a unit, and which implies that 7 has an inverse. So which is that inverse? That inverse is 13. So 7 times 13 is 91, which is congruent to 1 mod 15. 15 6 90, mod 15 is 1. Okay, so that is ideal. Now, with respect to this itself, we can see that as a general statement, we can say if an element generates the entire ring it implies and is implied by A belongs to R is a unit. That means element generates an ideal which is the entire ring, then it is a unit. Or in other words, if an element is a unit, then it will generate the entire ring as an ideal. So how do we show that? Let A belong to R and ideal generated by A is equal to R. What this implies is that since A generates the entire ring, that means 1 belongs to the ideal A, which implies that there exists an element R belonging to R such that A times R is equal to 1. Since every element of R is a multiple of A, right? So R will be an element of the ring. So we are going to substitute it one by one, 1, 2, 3, 4, 5, right? So it will always be a multiple of A, which implies that A is a unit. Now, conversely, we start with A belonging to R is a unit, which implies what? Since it is a unit, there exists an element R belonging to R such that A times R is equal to 1. Since A is a unit, that means A times some element of R is equal to 1. So, which implies that 1 belongs to the ideal A or ideal generated by A. So, 1 is there. Now, let B belong to R, another element, which implies B is equal to B times 1 belongs to the ideal generated by A, right? So, which means R is a subset of A. Now, how can we say that R is a subset of? See, we have a specific element belonging to R, which is a unit. Because of that, we have a particular another element R such that AR is equal to 1, which means 1 belongs to A. Now, since 1 belongs to A, let B be an arbitrary element of R, which means what? B can be written as B times 1. So B times 1 belongs to A because 1 belongs to the ideal and B belongs to R. So its product belongs to A. So we have found at least 3 elements of R which belong to the ideal A. So which means R is a subset of the ideal generated by A. So, but we know that an ideal is a subset of the ring R. That is, ideal is a subset of R. So, which means since R is a subset of A and A is a subset of R, implies that the ideal generated by A is equal to R. So, we have shown both sides. If the ideal generated by A is equal to R, then A belonging to R is a unit and vice versa as well. If A belongs to R is a unit, then the ideal generated by A is the entire ring. Okay, another very interesting thing is every ideal of Z is a principal ideal. Okay, now let I, that is the ideal, be a subset of the ring of integers is an ideal. Now let n belong to I, where n is the smallest non-zero positive number. Okay, so which implies that I can be generated by n. Now remember, we have already seen we have generated some ideals with respect to some rings. So we know that the ideal generated by n would be a subset of I. See, if we go back, you will notice here 2 generates the entire ring, but there are other elements which generate a subset. So that is why I'm saying as a general statement that n will generate an ideal which would be a subset of the ideal generated by the element which generates the entire ring. So M be an element of I. So let's say now using the division algorithm, M is equal to NQ plus R, where R is between N and 0, 0 included. Okay. So here we can write this as R is equal to M minus NQ. So here you notice M belongs to ideal and a multiple of N belongs to ideal. So if they both belong to ideal, then the result would be ideal only when R is equal to 0. Because remember, you have a closure property. We can write this as M plus minus N, right? So it is closed under addition. Since it is closed under addition, this must be equal to 0. So which means M would be equal to NQ. Now since M is a multiple of N, implies that M belongs to the ideal generated by N, which in turn implies that the ideal is a subset of, or I is the subset of the ideal generated by N. So what do we have? We have the ideal generated by N is a subset of I, and I is a subset of the ideal generated by N. So which implies, or we can say therefore is equal to I. Now here we have basically taken it as if N is a positive number, right? It is not 0. So if N is equal to 0, then the ideal would be the set containing only 0. So this is our 0 ideal. Now another very important aspect is that here remember we took the condition as if R belongs to R and S belongs to S, then RS belongs to S and SR belongs to S. Now, in this case, it is called ideal or right and left-handed ideal. Now, it might happen that only one of the condition is satisfied. If only RS belongs to S, then in that case, it is called left-handed ideal or left ideal. If only SR belongs to S, then it is called right-handed ideal. And as we have seen, if both SR and RS belong to S, then it is called just ideal. So that is ideal of a ring. That's it for now. Bye.